This question was asked in the GATE Physics paper 2021. This is a MCQ type question having 2 marks, and this question was asked from the topic quantum mechanics, specifically from the chapter scattering theory. The question is, consider the potential U as a function of small r defined as U as a function of r equals to minus mu naught times e to the power minus alpha r divided by r, where alpha and u naught are real constants of appropriate dimensions. According to the first Born approximation, the elastic scattering amplitude f theta calculated with u as a function of r for a wave vector, that is momentum transfer q, and in the limit alpha tends to 0 is proportional to option A is given q to the power minus 2, option B q to the power minus 1, option C q, and the last option, option D, q square. So there are 4 options given. We have to choose the correct one. And one important information is given in the question, that is useful integral. Integration from 0 to infinity sine qr times e to the power minus alpha r dr equals to q by alpha square plus q square. So this integration will be required to evaluate the correct answer for this question. Okay, let us see the solution part now. Before going to the main part of the solution, we will be discussing some important concepts regarding scattering theory in quantum mechanics, which will be highly useful to solve this problem. Then let us start. Let us consider a beam of particles having each of mass small m. They are traveling along the z-axis with some velocity v. Now we'll be considering the incident particles as free particles. So the particle wave will be incident plane wave, and the plane wave will have a wave vector k naught. Now the incident particles will be scattered by scattering potential or target potential V. This target potential may come due to the target material kept at the origin or at the center. Now when the incident particles will reach near the target potential, they will experience a force. Now the range of the scattering force will be effective up to a distance r naught. So this effect of the scattering potential will remain in the sphere having radius r naught, where r naught is known as range of scattering potential. Now, due to the interaction of the incident particles with the scattering potential, the particles will get scattered in all the directions. After leaving the sphere, the incident particles move again along a straight line. So basically, when the beam of particles will be within this sphere of radius r naught, they will feel the effect of target potential. So they will experience a force and they will get scattered. But when after scattering, they will come out of this sphere, they cannot experience the effect of target potential there. So they will act as free particle outside this sphere of radius r naught, and they will move along the straight line. The angle between initial and the final straight line is known as scattering angle, that is denoted by theta here. Now after scattering, all the particles will be scattered in all possible directions in the sphere. So we will be considering a small region, basically a small differential solid angle d omega, through which the particles, some particles are getting scattered. So the cross section through which the some particles are getting scattered is dA equals to r square time the differential solid angle d omega, which is shown here by the dark region. So through this differential area dA, the scattered wave or particles will be scattered in d omega along theta and phi direction in the three-dimensional spherical polar coordinate. Till now, we have already seen when some incoming particles are reaching near the target potential or scattering potential V kept at the origin, the incoming particles will experience some scattering force due to the target material or target potential, and they will get scattered. So this scattering phenomena is basically happening due to the collision between the incoming particles and the target material. So this collision may be considered as two types depending on the phenomena. The two types of collisions are elastic or inelastic. Now the total number of collisions over the duration of the experiment is proportional to, first one is total number of incident particles, and second one is number of target particles or target potentials per unit area in the path of the beam. Now the number of particles scattered into an elementary solid angle d omega equals to sine theta d theta d phi is proportional to a new quantity, that is differential cross section, and mathematically that is denoted by d sigma d omega as a function of theta and phi in spherical polar coordinate. Now let us see what does it mean by differential cross section d sigma d omega. So it is defined as the number of particles scattered into the elementary solid angle d omega, that is sine theta d theta d phi, in a direction theta comma phi per unit time and per unit incident flux. Now the incident flux means the number of incident particles per unit area per unit time. Till now, we have already discussed about the differential scattering cross section d sigma d omega in a scattering experiment. And also we have discussed the definition for the differential scattering cross section. From the definition, we can construct a mathematical relation between the d sigma d omega and the incident flux, that is J in, and the number of particles scattered into elementary solid angle d omega, that is dn, as a function of theta comma phi. So this mathematical equation tells us d sigma d omega as a function of theta comma phi equals to 1 by J in times dn d omega as a function of theta comma phi. Here J in is the incident flux, that is number of incident particles per unit area and per unit time, and dn as a function of theta comma phi is the number of particles scattered into the solid angle, elementary solid angle d omega, that is sine theta d theta d phi, in a direction of theta comma phi in the spherical polar coordinate per unit time. Now if we know this differential scattering cross section in a scattering experiment, then we can calculate the total scattering cross section in that experiment, and this total scattering cross section is given by sigma t equals to integration of d sigma d omega over the entire solid angle. So this integration will run for theta and phi, and theta ranges from 0 to pi and phi ranges from 0 to 2 pi in this spherical polar coordinate, and inside the integration we will have d sigma d omega times d omega will give this term sine theta d theta d phi. Now we will consider a special case. Our scattering potential is spherically symmetric. If we consider our potential is spherically symmetric, then for that the d sigma d omega will be only the function of theta. So d sigma d omega will not depend on the phi term. Hence, our total scattering cross section will also be the function of theta only, not phi. So for the special case, this total scattering cross section sigma t will be 2 pi times integration over theta equals to 0 to pi d sigma d omega as a function of theta sin theta d theta. Here 2 pi is coming for the integration of phi from 0 to 2 pi. Now the dimension for the differential scattering cross section and the total scattering cross section is area, and the typical unit used for this scattering cross section is barn. One barn is basically equals to 10 to the power minus 28 meter square. Now we'll be discussing briefly about the scattering amplitude. So basically, what will be the amplitude of the scattered wave when an incident particle beam or particle wave is getting scattered out due to the target potential or target material. At large distances from the scatterer, the effect of scattering potential is negligible. That we have already seen in the first slide. So basically there will be only the effect of scattering potential on the particles within some scattering potential range or not. Otherwise the particles will not feel the effect of scattering potential. The parallel beam of incident particles can be represented by the free particle equation, that is plane wave equation, that is given by psi incident as a function of r vector equals to a times e to the power I k naught dot r vector. Here k naught is the wave vector for the free particle wave. Now as the particle beam is moving along the z direction, we can write the wave function for the incident particles as psi incident as a function of r vector equals to a times e to the power I k naught z. So this is the equation of wave, plane wave moving along the z direction. Now before the interaction with the target, the particles with incident beam are independent of each other and they move like free particles with the momentum h cut k naught vector. Now when the incident wave collides with the target material, an outgoing wave is scattered out. In case of isotropic scattering, the scattered wave will be spherically symmetric. So then we'll have the scattered wave in the form of a times e to the power I k dot r by r. But in reality, the scattered wave is not spherically symmetric. Its amplitude depends on the direction theta comma phi along which it is getting scattered. Therefore, the actual scattering wave function is given by psi scattered as a function of r vector equals to a times scattering amplitude function, that is f theta as a function of theta comma phi times e to the power I k dot r divided by r. This is a spherically diverging scattered wave, and this f as a function of theta comma phi is known as scattering amplitude. Now for the case of spherically symmetric potential, that means our scattering potential only depends on the distance from the center, that is r, then our scattering wave function can be written as a times the scattering amplitude as a function of theta, that is f as a function of theta, times e to the power I k dot r divided by r. So for this special case, spherically symmetric potential, the scattering amplitude will be only function of theta, not phi. Here theta is the angle between the scattered wave vector k and the incoming particle wave vector k naught. Now, what is the relation between the differential scattering cross section d sigma d omega and the scattering amplitude f as a function of theta comma phi? The relation is d sigma d omega equals to k by k naught times mod square of scattering amplitude, that is f as a function of theta comma phi. Here k is the magnitude of the scattered wave vector and k naught is the magnitude of incoming or incident wave vector. Now for the case of elastic scattering, where the momentum and energy conservation holds, for that case k will be equal to k naught. So for the case of elastic scattering, d sigma d omega equals to mod square of scattering amplitude, that is f as a function of theta comma phi. Now we'll discuss about a approximation in scattering theory, that is first born approximation. So what does this first born approximation tell us? This approximation tells us if the scattering potential or the target potential V as a function of r vector is weak enough, or we can say the incident particle energies are larger enough than the scattering potential, then there will be slight distortion of the incident plane wave. In such case, we can approximate the scattered wave as plane wave. The scattering amplitude can be written as f as a function of theta and phi equals to minus mu by 2 pi h car square times integration of e to the power I k vector minus k naught vector dot product with r vector multiplied with v as a function of r vector, that is the scattering potential, times the elementary volume dq bar. Here mu is the reduced mass between the target material and the incoming or incident particle. And we'll consider this k vector minus k naught vector as q vector, which is known as momentum transfer vector. Then the integration will take the form minus mu by 2 pi h car square times integration of e to the power I q vector dot r vector times v as a function of r vector times the dq bar. Okay, then we can take the mod of q vector, that is basically mod of k naught vector minus k vector, which will give root over mod of k naught square plus mod of k square minus 2 times mod of k times mod of k naught times cos theta. Here theta is the angle between k vector and k naught vector. Now for the elastic scattering, the k equals to k naught. So we can take the k squared term inside the square root to the outside. So it will give a k term outside the square root, and the remaining term inside the square root will be 2 minus 2 times cos theta. From the trigonometric formula, we know 1 minus cos theta equals to 2 sine square theta by 2. If we put that, then finally we will get mod of q equals to 2 times k times sine theta by 2. Now we have k vector minus k naught vector equals to q vector. If we take the dot product with r vector both sides, then it will give k vector minus k naught vector dot product with r vector equals to q times r times cos theta, where theta is the angle between q vector and r vector. Now for spherically symmetric potential, v as a function of r vector will be v as a function of r. That is the distance from the origin. For spherically symmetric potential case, the scattering amplitude f will be only function of theta, and that can be written as minus mu by 2 pi h car square times integration of e to the power I q r cos theta times v as a function of r times the volume element will give r square sine theta dr d theta dy. Now we have the expression for the scattering amplitude f as a function of theta for the spherical potential case. So in this expression, there is no term involving or as a function of phi. So the integral over phi will give only 2 pi here. We have the integration over theta from 0 to pi of sine theta e to the power I QR cos theta times d theta. So this we can write it as minus 1 by I QR times integration of 0 to pi e to the power I QR cos theta times d of I QR cos theta. So basically this d of IQR cos theta will give minus IQR times sine theta times d theta, and that minus minus will give plus and IQR will get cancelled out. Basically as a result we will get this expression. So basically we have rearranged this integral like this. So the integration over theta from 0 to pi sine theta e to the power I QR cos theta can be written as minus 1 by I QR times e to the power I QR cos theta. The boundary conditions are theta is equal to 0 to theta is equal to pi. So this will give minus 1 by I QR times e to the power minus I QR minus e to the power I QR. So this can be written as 2 by QR times e to the power IQR minus e to the power minus IQR by 2i. Now from the complex number theory you know this term will give sine QR. So this integral or integration can be written as 2 sine QR by QR. So if we use the integral performed in the last slide in the expression for the f as a function of theta, then we'll get this final expression for the f, that is f as a function of theta equals to minus 2 mu by h car square times q integration over r from 0 to infinity r sine qr times v as a function of r times dr. So this is the expression for the scattering amplitude under Born approximation for spherically symmetric potential. Now coming to our question. In our question it is given that the scattering potential u as a function of r is given by minus u naught times e to the power minus alpha r divided by r. So you can see this potential is spherically symmetric because only this potential is depending on the small r. So we'll put this scattering potential inside this expression. So we'll get the scattering amplitude f as a function of theta equals to minus 2 times mu by h car square q times integration from 0 to infinity r sine qr times minus mu naught e to the power minus alpha r divided by r, that is the scattering potential, times dr. So r and r will get cancelled out here. So our f as a function of theta becomes 2 times mu times u naught divided by h car square times q times integration of 0 to infinity sine qr times e to the power minus alpha r dr. Now it is given in the question the integration from 0 to infinity sine qr e to the power minus alpha r dr equals to q by alpha square plus q square. So we'll use this result here. Then we'll get f as a function of theta equals to 2 times mu times u naught by h car square q times q by alpha square plus q square. So q and q will get cancelled out from the numerator and denominator. So finally we'll get f as a function of theta for that given potential equals to 2 times mu times u naught divided by h car square times alpha square plus q square. So in the limit of alpha tends to 0, we can put alpha equals to 0 here. Then the f as a function of theta will be 2 mu u naught divided by h car square times q square. So basically in that limit the f as a function of theta proportional to 1 by q square, that is q to the power minus 2. Hence, the option A is the correct answer for this question. So, we have already discussed the important concepts required to solve this question, and we found that the elastic scattering amplitude calculated with the potential u as a function of small r, that is given by this, for the wave vector or momentum transfer small q and in the limit alpha tends to 0 is proportional to option A, that is q to the power minus 2.